All right, so let's get started. So in this chapter, we're going to talk about equilibrium. So uh, equilibrium is the situation when when the net force and the net torque on a system both vanish. So F net equals 0 and tau net equals 0. That's all there is to it. That is equilibrium. So we have seen many examples of F net equals 0 when we were doing problems on chapter 4 and 5. And we've also seen examples of the net torque being 0 in doing the problems on torque. So you have seen both of these situations before. We just didn't call it equilibrium at that time. So the concept of equilibrium is not new at all. Right? There are some good examples in the textbook. I would highly recommend looking at these examples, 11.3, 11.4. Okay, now let me just clarify one thing. We know that Newton's second law says that the net force is equal to mass times acceleration, right? And the net torque is equal to I times alpha. Okay. Now, if the net force is equal to 0, so equilibrium means that F net equals 0 and tau net equals 0, right? So F net equals 0 implies from Newton's second law that the acceleration is 0, and tau net equals 0 means that the angular acceleration is 0. Now, acceleration equals 0, does that mean that the object is at rest? The answer is no. If the acceleration is 0, means that the object could be at rest, but what it really means is that the velocity of the object is constant. This is all stuff that we've talked about long time ago. So acceleration equals 0 means that the velocity is constant. So the object could be at rest or it could be moving with a constant velocity. Both of these are possible, right? And the angular acceleration is 0. All that means is omega is equal to constant. And that could mean that the object is not rotating, it's at rest, or it's rotating with a constant omega. So both of these are possible, right? And just in case you are concerned about where I got the fact that v equals constant and omega equals constant, that should not be surprising you at this point. But that's just because A is defined as the dv dt. And alpha is defined as d omega dt. Okay. All right. Now, so the velocity being constant, for example, means that as I said, it could mean that the object is at rest or the object is moving at a constant velocity. Because when it's at rest, the velocity is 0 and that's constant. So it's all included over there. So if the object is at rest, then we call that static equilibrium. And this is just terminology. And if the object is moving with a constant velocity or rotating with a constant angular velocity, constant non-zero v or omega, so that means the object is either moving with a constant velocity or rotating with a constant angular velocity, or both. It might be moving with a constant angular velocity and at the same time rotating with a constant angular velocity. In both cases, A would be 0 and alpha would be 0. These cases are called dynamic equilibrium. But this is all terminology, and mathematically you treat all these cases the same way. All right. So that's pretty much all there is to the entire idea of equilibrium. All right, so you all have experience setting up equations, the F net equals 0 type of equations. You've done that many times in chapters 4 and 5. There is absolutely nothing new about that at all. I just want to talk a little bit about how you set up the net torque equals 0 equation. Okay. This is the only thing that might be slightly new to you. Okay, now when we calculated torque in chapters 9 and 10, we usually calculated the torque about the axis of rotation. So the axis of rotation was our reference point from which we calculated the lever arms and found the torques. Now, in equilibrium problems, you can calculate the torque about any point you want. It does not necessarily have to be the pivot point about which the system is rotating. You can calculate the torque about any point you want. So that leads to the question, which is a good reference point for calculating the torque? Which point should you choose as your reference point? Well, the answer is you want to choose a point through which there are a number of different forces passing. Why is that? So to see that, let us choose this point O. So we have a system here on which is just a bar on which a number of forces are acting. So F1, F2, and F3 are acting on the right end of the bar, and let's call this point O. The weight of the bar is acting down at its center of mass, and let's just call the length of the bar L. And another force, F4, is acting at the left end of the bar upwards. We want to calculate the net torque on this bar, and I'm claiming that the point O is a good reference point to choose. Let's see why. So let's first try to calculate the torque of F1 about the point O. Remember, what is torque? Torque is force multiplied by lever arm, and lever arm is simply the perpendicular distance from the reference point to the line of action of the force, right? So this is all stuff from chapter 9. So what is the lever arm of O about the point F1? So you would draw a line through F1 as we did in chapter 9. And then you would make a perpendicular from O onto that line, but clearly that perpendicular would have zero length because O is on that line, right? So the torque of F1 about the point O would be 0. Similarly, the torque of F2 about the point O would be 0, and the torque of F3 about the point O would also be 0. So none of these forces, F1, F2, and F3, which pass through the point O, have any torque relative to O. So that tells us that O is a good reference point to choose because it's going to make your net torque equation very simple. You don't have torques of 3 of the 5 forces just vanish. So what is our net torque equation then? We don't get any contribution from F1, F2, F3. Those forces don't have any torque about O. mg would have a torque. F4 would also have a torque. So before we write down our equation, we also need to come up with a sign convention. You can choose any sign convention you like. You can choose clockwise is positive if you like. Doesn't matter. So now let's ask ourselves, what is the direction of the torque exerted by F4? The answer is F4 is exerting a clockwise torque. Do you see why? If you're having trouble seeing why, just think about the bar, forget about all the other forces, and think about the reference point O and F4. So we are only considering F4, the bar, and the reference point. That's all. Forget about everything else in this diagram. Which direction is F4 trying to rotate the bar about the point O? The answer is in the clockwise direction, right? And so that's how we know that F4 exerts a clockwise torque, and the direction of F4 and the sign that we need to give that torque is positive according to our sign convention. So the torque of F4 would be F4 multiplied by L. What is the torque of mg? Is it a clockwise or a counterclockwise torque? So by itself, mg is trying to rotate the beam in the clockwise direction. So it's going to be in the counterclockwise direction. So mg is exerting a counterclockwise torque, and so it should get a negative sign. And what is the magnitude of that torque? Force multiplied by lever arm. The lever arm is clearly L over 2 for mg, and so it's going to be mg times L over 2, and that's it. So since we chose O to be our reference point, it was much simpler to we got a much simpler equation for the net torque equals 0 equation. If you had chosen some other reference point, like if you had chosen the left end of your bar to be the reference point, then the torque of F4 would have been 0, but the torques of F3, F2, and F1 would have been non-zero. And so you would have had a much more complicated equation for net torque equals 0. That is why it's important to choose a good reference point in calculating torques. All right. What we're going to do next is just look at a few examples of problems. So let's start with this one. I think there's a very similar problem to this in your mastering physics. Okay, so what you have here is that you have this you have a diving board set up, and there is a person who's standing at the end of the diving board, right? And you're given the length of the board, you're given the distance between the two pillars, and you have to find the magnitude and the direction of the force exerted on the diving board by pillar A, and the magnitude and the direction of the force exerted on the diving board by pillar B. Okay, so let's think about this problem. So we have, so let's draw the diving board. So these are the two pillars, and here is the diving board. And here is our person. We'll just draw the person as a point mass. Okay. So let's think about the direction of the force exerted on the diving board by pillar A. Remember that the board is attached to the two pillars, right? It's attached to the two pillars. So now let's think about what is the direction of the force exerted by the diving board A on the pillar. Can you think about that? Is it upwards or downwards? Well, the answer is, to figure out the answer, you would think like this. Imagine that A is not attached to the diving board, right? Imagine that this end of the diving board is just placed on the pillar. The left end of the diving board is just sitting on the pillar. It's not attached. What would happen if somebody were standing at the other end of the pillar? Obviously, the pillar would rotate and this end would take off, right? And the person would fall off. That is not happening. So if that is not happening, what must be the direction of the force exerted by A on the diving board? The answer is A must be pulling down on the diving board to prevent it from rotating in the clockwise direction. So from there you can conclude that the force exerted by A is in the downward direction. So this red arrow shows the direction of the force exerted by A on the pillar, right? And how did I figure that out? I just asked myself, what would happen if there was no force? If there was no force between A and the pillar? The answer is, if there was no force between A and the diving board, the answer is that the diving board would rotate and the person would fall off. But that's not happening. The diving board is staying in place. So A must be exerting a downward force on the diving board. So we know that in this particular situation, A is exerting a downward force. And how is it exerting a downward force? It's glued to the diving board, and so the force of that glue is pulling downwards and making sure the diving board does not rotate. All right. The second thing that we are going to figure out without doing any calculations is what is the direction of the force exerted by B on the diving board. Well, just imagine that B is not exerting any force. So just imagine for a moment that B is made up of plywood or paper, right? A is a real solid pillar made of cement. You have a solid diving board, heavy diving board, but B is just a pillar that's made of plywood or paper, like it's very soft, it can't exert any force. So in that case, what would happen the very next moment? So what would happen is that B would get crushed, right? You have a heavy person standing at the other end of the board. The board would rotate in the clockwise direction again, it would rotate like this, and the person would hit the ground again, and the pillar B would be crushed. So that's not happening. So that is telling us that B must be exerting an upward force. So in this chapter, it's very important to figure out the directions of forces. And the easiest way to figure out the direction of a force is to just ask yourself, how would the system behave if that force were not doing its job, right? So since the system does not do what it would do in that case, you can tell what role that particular force is playing. So please feel free to pause this video and make sure that you fully understand how I concluded that A exerts a downward force and B exerts an upward force. All right, so now let's apply the equations of equilibrium. Net torque equals 0. And, net force equals 0 and net torque equals 0. Okay. We also need to choose our system. So our system is the beam, the diving board. And there are three forces acting on it, Fa, Fb, and Mg. We need a sign convention. So we could just choose, for signs, we could just choose upward is positive for forces. We also need a sign convention for torques. So we could just choose either clockwise is positive or counterclockwise is positive. It doesn't matter. We could just choose clockwise is positive. And those are our signs, right? So let's set up F net equals 0. All the forces are in the up-down direction. So we only need to set up F net equals 0 along the y-axis. So what equation do we get? So what we get is Fb minus Fa minus Mg is equal to 0. Okay. We are looking for Fa. So clearly this equation is not enough. Let's choose, so we have two unknowns here, Fp and Fa. So we cannot use this equation to solve for Fa. So clearly we need one more equation. That might come from net torque equals 0. Let's give it a try. So as we saw in our previous example, we have to choose a good reference point in order to calculate the torque. What is a good reference point? How about we choose, you can choose anything you want, but let's just try choosing the point where Fb is acting to be our reference point, right? So if we make that our reference point, let's call that O. If we make that our reference point, then let us calculate the torques, the sum of all the torques relative to that reference point. So we have the distances here. This distance is 1.6. And this distance will be 5 minus 1.6, which is what? 3.4. Okay, so now let's calculate the torque of all the forces here. So clearly Fb is not going to have any torque because it's passing through, its line of action passes through the point O, so it doesn't have any torque about O. What about Fa? So Fa, first of all, is it exerting a clockwise or a counterclockwise torque? Since Fa is acting downwards, about the point O, it's exerting a counterclockwise torque. And so that will get a negative sign according to our sign convention. So we get minus Fa times 1.6. And then what about Mg? So Mg is exerting a clockwise torque about the point O. So the torque of Mg should get a positive sign. And so the torque will be Mg times 3.4. And that is all that we have for torques. Fp does not have any torque about the point O. And we set that equal to 0. And so from now, we have two unknowns and two equations, so we should be able to solve for everything here. But it looks like from that second equation, we can immediately get what FA is, because you can immediately rearrange the second equation to get FA, and so you can just solve this equation and get FA. And then you can plug that into the first equation and you can get FB. Now, there is another way you could have gotten FB directly. Can you guess what that method is? You would just choose to calculate torques about this point. Let's call this point P. So if you calculate, so this is about O. Let's do net torque equals 0 about the point P, and I'll just do it over here so that you can see the figure. We are doing net torque about a new reference point P, right? So, and we are just doing this for practice. What is the torque of FA about the point P? Clearly, it doesn't have any torque, right? Because its line of action passes through the reference point. What is the torque of FB about the point P? The answer is it clockwise or counterclockwise? FB is exerting a counterclockwise torque about the point P. So it's going to be FB multiplied by 1.6, and counterclockwise should get a negative sign. So minus FB times 1.6. And then mg is exerting a clockwise torque, so about the point P. So mg should, the torque of mg should get a positive sign, so let's put that down, plus the torque of mg about P is going to be mg times 5. And that's equal to 0. And so from here you can just directly solve for FB. And obviously if you solve for FB from here and FA from the other torque equation, they will obviously satisfy the first equation. FB minus FA minus mg is equal to 0. So you can use any of these equations to solve for FA and FB. I mean any two of these equations to solve for FA and FB. Alright, so now let's look at an example of a more complicated problem. So there are two examples in my PowerPoint. One of them is the one on slide 5 with the climber, and then there is this one. So both of them are very similar, and just as an example, I'll just work through this one. Okay, so what we have here is a beam or a strut, and this beam is hinged onto the ground, and you have a weight hanging from the other end of the beam, and you have a cable which connects the beam to the ground, right? And the angles are shown. Okay, so, and the whole thing is in equilibrium. So what we have to calculate is the tension in the cable, and the horizontal and the vertical components of the force on the beam from the hinge. Okay. Now, the first thing that we want to do, so we approach these problems in a very similar way that we approach the chapters 4 and 5 problems on Newton's second law. So we follow pretty much the same steps. We identify the system, we identify all the forces, then we break up the forces into components, choose sign conventions, and then we apply Newton's second law along the x direction and the y direction. And one extra thing that we have to do in these problems is we also have to sometimes apply the net torque equation, net torque equals 0 equation. So that Newton's second law for torques, for rotational motion. All right, so our system clearly is the strut. And what are the different forces acting on it? Well, one force is clearly the force of gravity, which is acting down. Let's draw that. Okay, let's just assume that the length of this beam is L. So if I write it, I'll just write it over here. The The length of the beam is L. All right, what other forces are acting on it? At the right end of the beam, you have one tension acting from the vertical cable. Let's call this T1. And then you have the other tension from the cable that's going diagonally like this. So that's T, that's acting on it. All right, so then what about the hinge? So at the location of the hinge, there are two forces. One is a horizontal force, which is going to be to the right. So let's call that H, just for horizontal, right? And then there will be another force which is going to be perpendicular to the surface, and that is our old friend, the normal force. All right. Now, how do I know that the hinge, the horizontal force is going to be to the right? How do I know that it's not going to be to the left? To answer that, just imagine what would happen if these screws did not exist and the hinge was not attached to the ground at all. So imagine that this hinge is sitting on a completely frictionless surface and it's not screwed or it's not bolted to the ground at all, right? In that case, what would the hinge do? Which direction would the hinge move? It would move to the left, and the bar would just plop down on the ground. The hinge would move to the left if it were on a frictionless surface and it were not bolted to the ground. Since it's not moving to the left, we conclude that the hinge must be exerting a horizontal force which is preventing it from sliding to the left, right? And the horizontal force has to be to the right. Okay, so that is how. So those are all the forces that are acting on the beam, and we have to figure out how to apply Newton's second law in both the form F net equals ma and net torque equals I alpha. Okay, we can quickly figure out what this tension force T1 is going to be by applying Newton's second law to the hanging mass. So let's say that the hanging mass has mass capital M. So let's apply Newton's second law to this hanging mass. So what are the forces on the hanging mass? There is the tension T1, which is going to be at the other end of the cable, acting upwards. And there is capital Mg acting down like this. So if you apply Newton's second law to this yellow hanging mass, it's going to be T1 minus Mg, capital Mg, equals 0. I've just chosen a sign convention. Upward is positive and downward is negative. So you can see from here that T1 is just equal to capital Mg. So we know what T1 is, right? We can easily find it. It's 225 multiplied by 9.8. So whatever that comes out numerically, you have its value. All right. Now let's apply the equilibrium equations to the strut. Okay. So let's start with breaking the forces into components. And which force needs to be broken into components? So Fn and H and Mg are all either along the x-axis or the y-axis. T is the only one that needs to be broken into components. So let's make two components for T. Just use a different color for that. So one component would be going like this, another component would be going like that. Let's be clear about the angles. So phi is 30 degrees and theta is 45 degrees. Okay, so clearly this angle will also be 30 degrees. All right, so the diagram is rather complicated now, but hopefully it's clear. Okay, so now let's see. So this angle will be 30 degrees, and this little angle over here, what will that be? That will clearly have to be 15 degrees, so that the whole thing is 45 degrees and it matches theta, right? Okay, all right, so feel free to stop the video here and make sure it's clear to you why the angles have these values. All right, it's just geometry. Okay, so now let's apply Newton's second law. Before we do that, I might as well just write one other thing here. So the component of t, which is horizontal, will clearly be t cosine 30 degrees. And the component of t that is vertical will be t sine 30 degrees, but I really don't have room to write that. I'll just t sine 30 degrees. All right. Okay, so now it's time to apply f net equals 0. Oops. Let's apply f net equals 0, and we are going to do that along the x direction and along the y direction. Okay, so along the x direction, what equation do I have? So what arrows are pointing in the, what force arrows do we have in the x direction? It looks like we only have h, which is pointed to the right, and t cosine 30, which is pointed to the left. So h minus t cosine 30 degrees is equal to 0, and that's our first equation. What are the unknowns that we have here? So t is an unknown. T is an unknown, h is an unknown, and fn is an unknown. So these are the three things that are unknown. So that gives us a heads up that we're going to need 3 equations for 3 unknowns. Okay, so we've got one. Let's see what we get from the y direction. So the y direction, in the y direction, what forces do we have? So we have the fn acting upwards, we have mg acting downwards, then we have t sine 30 also acting downwards, and then we have t1 acting downwards. And that's all. Is that correct? Fn acting upwards, mg acting downwards, t sine theta and t1 acting downwards. So that's one equation we're getting from the, so that's the second equation that we get from f net equals 0. So we have t1 is a known quantity. So again, we have an equation which gives us a connection between fn and t. Right? All right, so we need one more equation. That would come from net torque equals 0. Okay, now when you're doing the net torque equals 0, notice that we had broken up the t into 2 components, t sine theta and t cosine theta. You have 2 choices here. You could continue to work with the components of t and calculate the torques of t sine theta and t cosine theta, or you could work with t and then just forget about the components of t. So please don't do both. So do one or the other. So either work with the force or work with its components, right? Both of these approaches will give you the same answer. So in favor of just having one less torque to calculate, we are just going to work with t and not with the components of t, right? Okay, so let's first decide what is a good reference point for calculating torques. Clearly, it looks like Fn and H both pass through the hinge, and the hinge is also the natural pivot point of the system. So it looks like the hinge is a good point for calculating our torques. So let's just make that our reference point. So, reference point is right here. Okay. We're going to do net torque equals 0. Fn and H don't have any torque about the hinge because they pass through the hinge. So the first torque that we're going to calculate is the torque due to mg, right? So the torque due to mg, let's think about how we're going to get that. Can we use force multiplied by lever arm. The lever arm of mg, and this will just make the diagram even more cluttered. The lever arm of mg, to find that you would draw a line through mg, and then you would find the perpendicular distance from O to that line, and that distance is not immediately given in this problem, right? So we've seen in chapter 9 that in that case you just switch over to the other formula, which is torque equals Rf sine theta. I'll just write that over here, torque equals Rf sine theta. R, to remind you, is the distance from the reference point to the point of application of the force. So R would be this distance, right? Which is L divided by 2. Now, I don't know what L is yet, but I'm just hoping for the best, that it ultimately cancels out or something. So let's just push forward and write down the equation for the torque of mg. I mean the expression for the torque of mg. It's going to be force, so it's going to be R, which is L divided by 2. Okay, L divided by 2 multiplied by the force, which is mg, multiplied by sine of the angle between mg and R. And in this case, the angle is going to be 45 degrees. It's going to be this angle. And that's going to be 45 degrees. So L over 2 mg sine 45 degrees directly from Rf sine theta. Okay, the next torque that we are going to calculate is going to be the torque of, maybe I should just write the torque equation over here. The problem is, oh, I can resize the figure. Okay, so yeah, maybe that's better. So the next equation, so I'll just rewrite the torque equation over here. Okay, so what we have so far is L over 2 mg sine 45 degrees. Okay, what do we have next? The torque of T1. So T1 is acting downwards just like mg is. So and we also need a sign convention for torques. So the sign convention, you can choose whatever sign convention you like. We could just choose clockwise is positive. So it's just going to be plus T1 times L times sine 45 degrees. Okay. All right, so then there's one more torque that we need to calculate, which is the torque of the tension T. So we are going to use the same formula. The R would just be L again. And is T exerting a clockwise or a counterclockwise torque? So T is trying to pull the beam, rotate it in the counterclockwise direction. So T is exerting a counterclockwise torque, and so it should get a minus sign. So it's going to be L multiplied by T multiplied by sine of 15 degrees. And that's all the torques that we have. And that is equal to 0. Now what about the L? Thankfully, it looks like you can divide both sides by L, and the L will just cancel out. And so we did not need to know what L was. All right, so we have three equations, equation 1, equation 2, and equation 3. And three equations and three unknowns, so you can just solve for T, H, and Fn. Now you might be thinking that, oh my god, so it was so much work just getting the three equations, and now we have three simultaneous equations. Simultaneous equations, you might remember from middle school or whenever you learned them, are typically a lot of work, especially if you've got three unknowns. But the equations that you get in these problems are typically very easy to solve. For example, if you just look at this last equation that we have here, what is the only unknown? The only unknown is t, right? You have a numerical value for everything else. So you can immediately solve the third equation and get t, right? Really easy. Once you have t, you can plug that into the first equation and solve for h. And then you can also plug that into the second equation and solve for y. So even though you have a system of three simultaneous equations, the good news for these problems is that it's usually a very simple system of three simultaneous equations. It's not bad you don't need a fancy calculator to solve them at all. Okay, so from these equations you can just solve for Fn, h, and t. And that's how you do all these problems. Okay. I'm going to briefly talk about center of gravity. So the center of gravity of an object is the point where the weight, which is the gravitational force on the object from the Earth, might be considered to be acting. In reality, the weight of an object acts individually on every atom and molecule, every particle that the object is made up of. But that's very difficult to imagine. Just thinking of an practically infinite number of particles that the object is made up of, each of them individually feeling the gravitational force. So it's much more convenient to just imagine that the gravitational force is just one force which is acting at one point on the object, and that one point is what we call the center of gravity. Now, what is the difference between center of mass and center of gravity? The difference is the following. The gravitational force is not exactly the same for every point on the object. We are going to see in chapter 13 that the force of gravity is depends on the distance of an object from the center of the Earth. So the greater the distance from the center of the Earth, the weaker the force of gravity. So if an object is sitting on the ground, the gravitational force at this point is not exactly the same as the gravitational force on this point. So each point in the object feels slightly different forces of gravity. And so you have to do the calculation for center of mass a little bit differently. And in that case, the center of the point that you get where you can imagine the entire force of gravity to be acting is a little bit different than the case than the point that you get for center of mass. However, this difference is only academic because the gravity near the surface of the Earth is more or less constant. So for all practical purposes, if the object is a regular sized object like a building or a hill or something like that, or a person, the gravitational force over here is, for all practical purposes, the same as the gravitational force over here. So there is hardly any difference at all between the center of mass and the center of gravity. Even for Mount Everest, the center of mass is a few centimeters away from the center of gravity. So for the rest of this discussion, we are going to treat the center of mass and the center of gravity to be the same point. And so I'm just going to refer to them synonymously. All right, so the next thing that we're going to talk about is the stability of equilibrium. So as you know, equilibrium means that the net force equals zero and the net torque equals zero on the system. There are actually two kinds of equilibrium. One is called stable and the other one is unstable. So what is stable equilibrium? Stable equilibrium means that a system is originally in equilibrium. You disturb the system a little bit, and then you find that it just comes back to equilibrium, right? So a small disturbance from the equilibrium, a small displacement from the equilibrium just brings the system back to equilibrium again. Unstable equilibrium is when you displace the system from equilibrium a little bit and you find that the system no longer comes back to equilibrium. So let me illustrate this with a few examples. And this is actually something that you're very, very familiar with. So the easiest example of stable equilibrium is to just consider a bowl. So if you have a bowl and you put a marble at the bottom of the bowl, um, the marble is in equilibrium, right? Why? Because there is a force mg acting downwards and Fn acting upwards, and Fn minus mg would be equal to 0 because it doesn't have any acceleration. So Fn would be equal to mg and the system is in equilibrium, right? What happens if you slightly displace the marble? So if you slightly displace the marble and move it over here, oops, it will just roll back, and it will eventually, it might roll around for a little bit, but eventually it will come back to equilibrium. So a small displacement from equilibrium in this case brings the results in the system coming back to equilibrium. So this is an example of stable equilibrium. What's an example of unstable equilibrium? You probably guessed it yourself. If you invert the bowl and carefully balance the marble at the top. Now, if you've managed to balance the marble and it's just sitting still, then it is in equilibrium. Mg is still equal to Fn. But the moment you displace the marble by a tiny amount, it will be completely, the equilibrium will be completely spoiled and the marble will just roll down, right? So what causes equilibrium to be stable or unstable? If you look at it a little more carefully, you will notice, let's just go back to the stable equilibrium case and analyze the forces over there. So when you displaced the marble, what were the forces on the marble? So you had mg acting down as usual, but Fn was acting in this direction, perpendicular to the surface, which is the bowl. So Fn had a component, actually not Fn, but mg has a component like this and another component like that. So you can see that there is one component of mg which is pointed back towards the equilibrium position, right? So this is called a restoring force. So a restoring force is simply a force. You can force which brings the particle back, brings the system back to its equilibrium position. That's why it's called a restoring force. And this component, the component of mg, the tangential component of mg, is providing a restoring force, and so the system is able to come back to equilibrium, right? What happens when we do the same analysis for the unstable equilibrium? So once it's displaced, mg is acting down like this. Mg will have a component, okay, just to make the colors match. I'm just trying to press the undo button, but it's not working. Let's try the erase. Okay, that's better. So mg is acting down. Let's break up mg into components. So there will be one component. Okay, what's the other force? The other force is just Fn. Perpendicular to the bowl. Mg can be broken up into two components, one in the radial direction and the other in the tangential direction. Sorry. Okay, so you can see that the tangential component of mg now is trying to take the marble away from its equilibrium position. So there is no restoring force in this case. And so the particle, the system, never comes back to equilibrium. So hopefully that is clear. So equilibrium, stable equilibrium is characterized by the presence of a restoring force which shows up whenever the system is displaced. So let me write that down. In stable equilibrium, a restoring force shows up. And I should clarify one thing here. It's not just a restoring force. It could also be a restoring torque. So a restoring force or a torque shows up when the system is slightly displaced bringing the system back into equilibrium. So that is what happens in stable equilibrium. Okay, now let's look at some more examples of stable equilibrium. So another example would be if you have a top-heavy object. So just imagine this this triangular object. Okay, let's say the center of mass of the. Let me just make this a little thinner. Okay, so the center of mass of this will be somewhere over here, where you have more mass, right? All right, now is this in stable or unstable equilibrium? What would happen if you slightly tilt it? So this is the ground. If you were to slightly tilt this, so let's draw the tilted version of this. It would look like this. I'm trying to keep the shape the same. Okay. And its center of mass would probably move over here. All right, so just imagine that these are the same shape. So is this stable or unstable equilibrium? From experience, you know what the answer is. This is stable equilibrium. But let's see if we can analyze it and understand it. So what were the forces on the on this object when its base was when it was just lying on the undisturbed? So there were two forces. One was mg acting down, and the other one was the normal. They're both acting at the center of mass of the object, and so the object was in equilibrium. When you tilted it a little bit, mg is acting down like this, still acting down from the center of mass. But what about the normal force? The normal force is now acting through the right corner, because that's the only point that's in touch with the ground. So the normal force is acting from the right corner up like this. So if you consider the point, the right corner over here, let's call that the point O, what is the torque? What is the net torque about that point? So Fn is passing through the point O, the right corner, and so Fn doesn't have any torque, right? But what about mg? Mg is acting at the center of mass. The new center of mass is indicated by the yellow dot over here. And what is it a clockwise torque that mg is exerting, or a counterclockwise torque about the point O? If you think about it, the answer is mg is exerting a counterclockwise torque, because just by itself, the weight mg is trying to rotate the system counterclockwise about the point O. So a counterclockwise torque is just what we need in order to bring the system back to equilibrium, right? So there is a restoring torque in this case. Which means that this is stable equilibrium. Let's quickly analyze the converse situation. Suppose I take the same top heavy object, same object, and make it top heavy. I made it bottom heavy this time, but let's make it top heavy. So that means it would kind of look like this. And the center of mass would be much higher up over here, right? Suppose I tilt this object a little bit. So, all right, so let me see if I can draw this. So I've tilted, so now the base looks like this. It's exactly the same object. So the center of mass has now moved somewhere over here, right? Okay, let's see what the forces are after the tilt. So before the tilt, it's same as the previous case. Before the tilt, the forces were mg and Fn, both acting through the center of mass. After the tilt, mg is acting down at the center of mass as usual. And Fn is acting right here at the contact point. That's the only place where it's making contact with the ground. Let's analyze torques about the right corner again, O. And Fn, as usual, does not exert any torque about the point O. What about mg? Mg is exerting a torque, but is it a clockwise or a counterclockwise torque? If you think about it carefully, you will see that it's a clockwise torque, because by itself, mg is trying to rotate the system clockwise. So clockwise torque is actually bad for the system in terms of equilibrium. It will destroy the equilibrium, right? So clockwise torque will not help the system come back to equilibrium. It will do the opposite. It will just make it go the other way. So there is no restoring torque, and so this is unstable equilibrium. All right. So the definition of stable equilibrium versus unstable equilibrium is that if you slightly displace the system, if it's stable equilibrium, a restoring force or a torque will show up, and that will bring the system back to equilibrium. If it's unstable equilibrium, there won't be any restoring torque or force. Worse, there might be a force or torque that takes you the wrong way, and the system will never come back to its original equilibrium state. Okay, now there is a very easy way to see whether a system is in stable or unstable equilibrium, right? And that is by just looking at the base of support, the original base of support of the system. So what is the base of support of our triangle here? The base of support, the original base of support means that the base that it's standing on, that's basically this, and it's this one over here. So the criterion to see whether equilibrium is stable or unstable is just to look at its center of mass and the base of support, right? So if you tilt it and the center of mass is still above the original base of support, like it is, let's call this diagram 1, and let's call this diagram 2. So if the center of mass is still over the original base of support, then the equilibrium will be stable, right? But if you tilt it a little bit and the center of mass is no longer over the original base of support, as you can see in diagram 2, the base of support is small over here, and the center of mass is no longer over it, then that will be unstable equilibrium and the object will fall over. So a very quick way of seeing whether an object is in stable or unstable equilibrium is to just consider the location of its center of mass and its base of support. So you can immediately conclude that if an object has its center of mass low, has a lower center of mass, then it's going to be more stable. Because you'd have to tilt it quite a bit in order to make the center of mass move past the base of support. If it's a top-heavy object like in diagram 2, then a small tilt will make the center of mass no longer be above the base of support and the object will topple. right? So wide bases, so if you want to make something stable, if you want to have stable equilibrium, as I say in the PowerPoint slide over here, so if you want stable equilibrium, you want a wide base and low center of mass or center of gravity will be most conducive to making the object stable. Here are some examples. This is the Leaning Tower of Pizza. It's actually pronounced pizza, even though the spelling is P-I-S-A. The pronunciation is P-I-Z-Z-A. Okay, so that's the Leaning Tower of Pizza. The base of support is you can see the base of support right here. The center of mass of the tower is going to be somewhere over here. And it's still above the base of support, so it's not in danger of toppling over. But unfortunately, this tower was built in absolute worst place where you can put a tower. The earth is very soft over there. And so the tower has a tendency of constantly sort of tilting. And so apparently there's a lot of efforts going on to prevent it from tilting further. Because as you can see, if it tilts more, then the center of mass has a chance of moving past the original base of support, and it will topple. Another example is this beautiful rock. This is called Balance Rock. I believe there's a state park named after it, the Balance Rock State Park in Utah. And it looks like this piece on the left is going to fall over, but it's actually, its center of mass is well over the base of support. Let me see if I can get a different color here. Its center of mass is well over the original, over the base of support, which is this. So it's not in danger of falling over. I'll show you a dramatic example of the center of mass of an object shifting beyond the base of support. Okay, so watch this carefully. Okay, so let's see what just happened. So she's sitting on the door of the refrigerator. She opens the door with herself on the door. And so the center of mass of the system consisting of herself and the refrigerator moves to a point which is no longer above the base of the refrigerator. And so the whole system topples over. Okay. Okay, so far we've talked about an object being in equilibrium. When an object is in equilibrium, the net force on that object is zero, the net torque on the object is zero. But that is really not the end of the story. So if an object is in equilibrium, it's quite possible that the object might get deformed. Right? You can very easily picture that. So suppose you have a piece of metal and you're exerting forces on it from opposite sides. These are equal and opposite forces. Then the object would be in equilibrium, right? Because the net force on it would be zero. But if the forces are large enough, then the object might get compressed. So that's just one example. We have other examples as well. So we're going to talk about this aspect a little bit. So far we've just talked about the forces being in equilibrium. We have not really talked about the effect that these forces are having on the object. That's what we're going to focus on now. So I'm going to introduce you to three terms, and I'm going to give you rather vague definitions to start with, and then just to give you an idea of what these terms signify, and then we'll talk about more precise definitions of these objects. Okay. So the first term that I'll introduce you to is stress. So stress characterizes the strength of the forces which are causing a deformation of the object, right? So if you have a lot of strong forces acting on the object, then you'd expect it to deform more, so the stress would be greater. Okay, now the next term that we'll talk about is strain. So strain characterizes how much an object is deformed. So if you apply more stress, then you would expect more strain. You'd expect the object to be deformed some more. Okay, now the third concept that I'll introduce you to is the elastic modulus. What is the elastic modulus? From experiments, it's found that the stress and the strain are linearly proportional to each other for most objects. So that means if you double the stress on an object, you will double the strain. So the stress and the strain are linearly proportional, and so you can define a proportionality constant. And that proportionality constant is called the elastic modulus, and it is defined as the stress divided by the strain. Now, mind you, I haven't really told you what exactly the stress is and how to calculate it, and I've also not told you how to calculate the strain, but I will in a moment. The elastic modulus is defined as the ratio of the stress to the strain. Now, there is one caveat here. When I told you that the stress is proportional to the strain, that is only true up to a certain extent. If you keep on increasing the stress, the object might be damaged, might be structurally damaged. In that case, you'll find that the stress and the strain are not proportional. Like once the object is structurally damaged, if you increase the stress even further, the strain might behave in some strange way, not proportional to the stress. And of course, if you keep on increasing the stress tremendously, then the object might just fracture. So our analysis is only restricted to the point where the stress is not that great, not so great as to structurally damage the object. So the stress is, so we are looking at relatively small stresses such that if you relieve the stress, the object will just come back to its original configuration. All right. So let's talk about more precise definitions of stress and strain. Now, the reason that I didn't give you these precise definitions earlier is because the precise definitions depend upon the context, like how the forces, what kind of forces are being applied and stuff like that. Okay, so stress is defined as, so let's consider this rod, right? The initial length of this rod is L0. That's what its length is. And let's say that you are applying forces in opposite directions. So we are looking at this figure here. You're applying forces in opposite directions. This kind of stress, where the forces are acting in opposite directions, is called tensile stress because you're causing tension. You're trying to stretch the object. It's called tensile stress. If you applied the forces in this diagram, if you applied the forces in opposite directions into the object, then you're compressing the object, and this is called compressive stress or compressional stress. Right? The definition of stress is the same for both of these situations. Right? So what is the definition of stress? Stress is defined as the force divided by the cross-sectional area of the sample. So F divided by A is the definition of stress. And this definition applies to both tensile stress and compressional stress. And A clearly is the cross-sectional area of the sample. All right. Now let's talk about strain. So as a result of applying the stress, either compressive stress or tensile stress, you will change the length of the object. Right? If you apply tensile stress, then you are going to stretch out the object. You're going to increase the length of the object. And if you apply compressive stress, then you're going to squeeze the object and reduce its length. Right? The change in length of the object divided by the original length is called strain. It's the definition of strain. So strain is delta L divided by L. In general, the strain is just, you don't take the sign of the strain into account. So the same definition applies to both tension and compression, and that's why you've got an absolute value around the delta L. Okay. So we have defined stress and strain for compression and tension. What is the Young's modulus that applies? What is the elastic modulus that applies here? The particular elastic modulus, remember elastic modulus is always stress divided by strain. The particular elastic modulus that applies here is called the Young's modulus. And the definition of Young's modulus is just stress divided by strain. Stress was F divided by A. Strain was delta L divided by the original length. And so that is the definition of Young's modulus. And Young's modulus is a measure of how easy or difficult it is to deform a certain material. Okay. And you have some examples of Young's modulus over here. I have an example of a problem here. This is basically just a plug and chug problem. And I'll let you look at it, work it out yourself. But let's just look at this problem together. I'll let you read it. So you are, so there are often certain situations in physiotherapy when you want to stretch out a certain bone. Right? And so what you do is, that's called traction. So traction is often helpful in, particularly in spondylosis. Traction is often, it is applied a lot. There are many other situations where it helps to stretch out or compress a bone. So in this particular example, the femur needs to be stretched out by a certain amount. Right? So you're given the percentage. So you're given the delta L divided by L that the femur needs to be stretched out by, and you have to find out the force necessary to stretch out the femur by that amount. So you can see how you would do it. You would just, and you can always look up the Young's modulus of the femur, and so that would simply be, so the equation would just, you would just start with the definition of Young's modulus. The Young's modulus, which you can look up from the table, is stress divided by strain. That's delta L divided by L. So the delta L divided by L is given. It's that 0.001% or whatever it is in the problem. And you're looking for F. You're given Y and you're given A. So you just plug and chug these into the formula and you would get the force necessary. Okay, so for this, for these topics, you can at most expect plug and chug problem. And I expect you to know what stress is, what strain is, and what the definitions of stress and strain are for the examples we're looking at. Okay, then the next type of stress that we're going to talk about is shear stress. Now, I will not be testing you on this formula. So for the shear stress, I only expect you to know it conceptually. So I'll not be testing you on this formula. So so I just want you to know it conceptually. So what is shear stress? Shear stress happens when you have two opposite forces acting on an object, and the object is still in equilibrium, but the forces are not acting in the same straight line. So here is one example. You've taken this book, it's sitting on a rough surface, and you apply a force on the book's cover, and so that causes, so the force due to your hand is acting in the towards the right, and the force due to the rough surface is acting towards the left here, and so the two forces are not in a straight line, and that causes the book to deform in a certain way. And this kind of deformation is called shear. Right? And these types of forces, which don't act in the same straight line, are called shear forces. There are many examples of shear forces. As I said, you can define a shear stress and you can also define a shear strain, but we are not going to get into those definitions at all. Okay. So I just want you to qualitatively know what shear stress is. One interesting example of shearing is scissors. So what happens with scissors? So suppose you're cutting a piece of paper or a piece of cloth with scissors. So what happens is that one blade of the scissor acts like this, another blade of the scissors right here. You know that the two blades of the scissors are slightly displaced. You can take a look at a pair of scissors and check yourself if you're not convinced. So the two forces act a little bit off. slightly displaced from one another. They are not in the same straight line. So they exert a tremendous shearing stress on the material, which easily ruptures the material. I'll show you one more example of shearing stress. Okay, so here is another example of shearing. So Hugh Jackman is applying, so I believe this is 465 pounds. So those of you that have some experience in weightlifting might be trying to figure out how much weight this is. But this is in Australia, and apparently they have completely different color, some weird color coding, which doesn't make sense to us over here. But I'm told that this is 465 pounds, so it's quite impressive, to me at least. So there are, if you look at the barbell, it's slightly bent, right? Why is it bent? It's bent because there is a force. I don't think I can draw on this. So this is the barbell, and so there are two forces due to the weights on either side, and two forces due to his arms. And so these forces are not in the same straight line. So the result of that is that the barbell is bent. And if you look carefully in the figure, in the photo, you can see that there is some bending of the barbell. And this quote here at the top is one of my favorite quotations. Most people's favorite quotations are from Shakespeare or Gandhi or Martin Luther King, but here is mine. And I'm not a particularly deep person, but anyway, okay. So that is shearing. The last elastic modulus that we're going to talk about is the bulk modulus. So the bulk modulus is relevant when you place an object inside a fluid. So when you place an object inside a fluid, there are forces, and we're going to assume that the object is not very large. But our discussion applies to a small sample. So when an object is placed in a fluid, there are forces on it from every direction, right? So the stress in that case is defined again the same way. It's force divided by area, or it's right here. This is the stress. As we will see in the next chapter, this stress is called pressure. So pressure is just defined as force divided by area. So this is just pressure. And as a result of this pressure, the volume of the object is going to change. The object will shrink, as you can see in this diagram. The object will shrink. So delta V will always be a negative number because the object is, if the force is really acting inwards from every direction, delta V is guaranteed to be a negative number since the object is guaranteed to shrink. So the strain is defined as delta V divided by the original volume, right? And so that's the definition. This is the definition of the strain. Why do we have a minus sign? Just because once it was conventional to define delta V where the object is contracting with a negative sign, right? And so to counteract that, a negative sign was included in the formula to make the bulk modulus positive. So that's just convention. If you wanted, you could have just put a absolute value sign around the delta V, but it's just conventional to write the formula like this. Okay, so the minus here is just in case you use a negative sign for delta V, the minus will just cancel that out and make B as positive. Right? But there's absolutely no harm with doing this. Delta P divided by absolute value of delta V divided by V0. I mean, this would have been absolutely fine. This would have probably made a little more sense, but it's just conventional to write it like this. There is one other thing. The compressibility K is defined as these three equal signs. Three lines means defined by 1 over the bulk modulus. The only reason why I'm mentioning this is because in mastering physics, there is a problem where you're given the compressibility, and it's basically just a plug and chug problem on the bulk modulus. But you're given the compressibility, so you just have to do 1 over that and get in order to get the bulk modulus.